Okay, so this is part 3 of the divergence theorem. So let's recall the divergence theorem says that the flux of F, so some vector field through S, is equal to the volume integral of the divergence of F over the region enclosed by S. So S here is a closed, piecewise smooth surface. Q is the region enclosed by S, and N here is the unit normal vector directed out of Q. So in the last video we proved the theorem for a rectangular box. So we showed this holds for a rectangular box. So in this video we're going to give an intuitive proof of the divergence theorem by making 4 observations. Okay, so let's start making these observations. Let me write observation 1 up here now. So let me erase this stuff and we'll write our first observation. Okay, so here's our first observation, which I think is the crucial observation. So it says if we stick 2 rectangular boxes together, the flux through the portion of the 2 faces that touch will cancel, since the normal vectors on the 2 faces there are in opposite directions. Okay, so let me demonstrate this. Okay, so let me explain this. So here's our 2 boxes stuck together. So let's look at the portions where they touch. So you're going to touch here and here, I've marked. Okay, recall now that the flux is how much fluid is flowing through this face relative to normal vector, and the flux here would be how much is flowing through this portion relative to normal vector here. But now, I recall in the divergence theorem, the normal vector is directed out of the region. So normal vector for this guy would be pointing that direction. Normal vector for this one would be pointing this direction. So the absolute value of the fluxes would be the same because they're touching. But the normal vectors are in opposite directions. That would mean that the fluxes in the portions where they touch will cancel. So hence we can say then that the flux of F through the new region, so through this region, will be the same as the sum of the fluxes of the boxes, so it'll be the sum of the flux of this one plus this one. Okay, so that's the critical first observation that we need to make. Okay, so pretty much we've shown then that the divergence theorem then will hold for this new stuck together box. So when you stick together 2 boxes, the divergence theorem will hold in this new region. Okay, let's write that as observation 2 now. So observation 2 is that the divergence theorem holds for the stuck together boxes, so it'll hold for this. So again, we've shown that the flux of F through this surface will equal the flux through this one and this one. And also the volume integral of the divergence of F over the region here will equal the volume integral of this guy plus this one. So you can see then the divergence theorem will hold for this new region. Okay, let's now write observation 3. Okay, so the third observation, so in general, the divergence theorem holds for the region created by stacking rectangular blocks. I guess we just showed it for sticking together 2 rectangular blocks or boxes, but in general you could stick together as many as you wanted to or stack them. So this is observation 3. Okay, so let you think about that. And now let's put observation 4. Okay, so the fourth observation, so any region that has a piecewise smooth boundary surface will be the limit of regions created by stacking smaller and smaller rectangular boxes. So from these 4 observations now, we can now conclude, so the divergence theorem now follows from these observations. So we've proven now the divergence theorem. Okay, so let me demonstrate this a bit more with an example. Okay, so suppose you want to prove that the divergence theorem holds for a rectangular pyramid. So what we can do is we can stack some rectangular boxes. Let me take some here. So I'll use these 4 as the base. Then I'll use some smaller ones up here. And one on the top here. So this approximates the rectangular pyramid. But if I use smaller and smaller boxes, the approximation will get better and better. And we know for each of the stacked regions, the divergence theorem would hold. So I can take the limit by letting the boxes get smaller and smaller. So in that limit, it will get closer and closer to the actual rectangular pyramid. So since it holds for all the stacked boxes, all the regions created by the stacked boxes, it will also hold for the rectangular pyramid. So that's the idea. Alright, so from those 4 observations then that we've made, we are able to prove the general divergence theorem. Okay, so I'm going to leave the video here. In the next video, we'll be looking at using divergence theorem to prove some properties about the divergence of f. Okay, so let's leave it here.